Hey, how's it going? This is Rob coming to you with a video on homework quiz number 2, Math 134, Spring 2020. Okay, so in this video, I'm going to talk about the homework quiz, talk about some common misconceptions, and explain how to do the answers to this one. This quiz covered sections 9.3 and 9.4. 9.3 was an introduction to the derivative, including, instantaneous rate of change and average rate of change and the idea of change and how that relates to the derivative. All right, we talked primarily about the limit definition of the derivative. All right, and then in 9.4, so in 9.3, right, we started with talking about the limit as h goes to 0 of f of x plus h minus f of x over h, right? And we talked about how this was essentially the slope of the tangent line. Okay, so we had that. The next thing we have is that we want to talk about is 9.4, and 9.4 broke us out of the limit rules because now we actually had those 4 rules: the power rule, the constant rule, meaning all constants you take the derivative, they're 0, constant times a function, and the sum and the difference rules. Okay, so that's what happened in 9.4. So because of 9.4, the rules we learned, we no longer have to use the limit definition every single time we calculate a derivative, though we are allowed to do that. In the lesson in which this quiz was given, I also talked about the product and the quotient rules, and I did note prior to beginning the quiz that if you want to use the quotient rule on this test, or this homework quiz rather, that is completely fine, because that is a completely valid way of solving it. And now that we have those tools, it's perfectly fine for you to use them. But that was not required. Okay, so I'm going to dive into the first problem here. I think the first problem is one that probably would require more discussion than the second problem. Okay, so this problem was attempted in a number of ways. All right. Some people, I'd say the small minority, but some people attempted to use the quotient rule. Good. Other people attempted to simplify it and then do it using the other rules that we learned. So those are the two broad methods. The one thing that I think was difficult is that people did not follow what I had said in class. Okay, so one of the biggest wrong answers that I saw was something along the lines of this. Okay, so I saw something like 6x squared minus 8x, something like that. Sometimes I just saw that. Sometimes I saw it over x. Sometimes I saw this. And sometimes I saw 6x minus 8. Okay? Which is the equivalent of this first one. Okay, so remember, one of the big things I said in class is that derivatives with quotients do not work this way. Think about it. If I could just differentiate the top and differentiate the bottom and have my answer, why would I need the quotient rule? What would that be useful for, right? If you think about it, the quotient rule exists in a sense because you simply cannot do that, all right? Because think about it, right? If I could just use the rules of derivatives that we learned prior, then yeah, you could get something exactly like this, but that's not how it works. And so when we do the answer, we're going to see this is not what we get. So the biggest thing coming out of this is you cannot do a quotient by taking the derivative of the top and the derivative of the bottom. It doesn't work in this context. There are times where you can do that, but it is not when you're doing differentiation, okay? So please, you cannot do that. That's one of the main reasons you do need to know one of the strategies, okay? Particularly either simplifying or using the quotient rule. So I'll do method 1. So here's how some people simplified. So they take everything and they divide it out by x. So if I divide 2x cubed by x, I get 2x squared because one of the x's cancel. If I divide 4x squared by x, I get 4x because one of the x's cancel. And then if I divide the 3 by x, well, the x doesn't go in, so what I get is 3 over x. And this is just the equivalent of 2x squared minus 4x plus 3 times x to the negative 1 power. Remember that we talked last time about how the x's, when it's in the bottom, that's indicative generally of a negative exponent. So because it's a negative 1, the x would go to the bottom and it would become a positive 1, just as you see here. Okay, so then if you use the power rule to get the derivative, okay, so you bring the power down, 4x. This one becomes minus 4 because the derivative of x is 1. So it's 4 times 1. Okay, then the sum and the difference rules allow us to add this up. Then here I bring down the negative 1. So it becomes a negative 3x. And this becomes a negative 2. So you could have left it like this. I would have accepted that. Given the relative difficulty that I threw in there, I would probably be okay with that. Alternatively, you could do something like this. Okay, that would also be correct. That's using this method. Now look, you can see that this is not any of these three things right here. Okay, these are right, but they're nothing like this. So you can see that you actually do get a very different answer if you take this approach rather than top divided by bottom. Now look, I'm not trying to put down people who did it this way, right? When you do the derivative of the top and the derivative of the bottom. I said in class that that's a tempting thing to do. And to many, it makes sense to do it that way. But that is not the correct way that you do these kinds of derivatives. So please, you need to find a better way to do that. Okay, method 2, quotient rule. Mostly executed correctly. So we have low. And I'm going to do the low in blue and the high in. How about we do the high in red? So low, and then here's my high. Now remember, it matters which one is which. Low is specifically the function on the bottom. In this case, x. Okay. High is specifically the function on the top. In this case, 2x cubed minus 4x squared plus 3. So here, let me just drop in my parentheses. So we have low and then d high minus high. And by the way, on a test, you are more than welcome to use multiple colors if that helps you. Okay? You're more than welcome to do that. Just the only thing I'd be concerned about probably is the time. But if the colors help you get to the right answer in a way that makes sense, I don't have a problem with it. All right, as long as you know, I just can't give you more time. So low d high minus high d low all over low squared, okay? And we proved this in class why you get this formula. So low d high minus high d low over the bottom squared, and away we go. Let's see what it looks like. So, all right, here I have my straight up. Let me just hook up this little skeleton of my problem so I can just fill in the color later. Okay. So here's what I've got. Low stays x, d high. So the derivative of this is 6x squared minus 8x, which a lot of people knew, right, if they did the derivative of the top. So that's valid. Okay, high, well, here it just stays the same. 2x cubed minus 4x squared plus 3. D low, what's the derivative of x with respect to x? It is 1 over low squared. So that's x squared. Okay. Now I'm going to distribute, and here I'm going to go back to black. So I've got 6x cubed. Okay. Minus, make sure we see this is a cubed, minus 8x squared. Now, here's the one thing I like. I'm really proud to say that 100% of the people who did it this way got your symbols correct. Very good job. So this stays the same because you're multiplying by 1, but now it becomes minus 2x cubed. Now look, you're minusing negative 4x squared. So it becomes plus 4x squared. Then you're minusing positive 3. So that's the one thing that I really loved about this. Very good job, because look, I would not blame you at all if you messed up the symbols, because it happens all the time with people of all ages and stages. But I'm proud to report that no one on the quiz messed up your symbols. So very good to those of you who did this. The one mistake I did see from I think maybe one person is, don't forget, if this is a squared, this still needs to be a squared. You're not taking the derivative here, so just double check that. Now you're going to have some like terms combine. Okay, in particular, I can see on the top 6x cubed. It's going to go with this minus 2x cubed. And then another like term I have is this minus 8x squared is going to go with this positive 4x squared. So we're going to have some like terms combined. So when I combine 6x cubed and a negative 2x cubed, I get 4x's cubed. Okay, when I combine negative 8x squared and 4x squared, I get minus 4x squared. And then the minus 3 becomes a minus 3, right? Nothing else to combine. And if we were to simplify this by dividing out, so these would cancel, you'd get 4x. Then these would cancel, you'd get 4. And then nothing can cancel here, so you get 3 over that. So you observe that this answer here and this answer here are exactly the same. Okay, meaning you could either have simplified or used the quotient rule. So again, this is simplifying. This is using the quotient rule. Okay, and remembering the quotient rule. Okay, if you have f divided by g, okay, the derivative of the quotient is low d high minus high d low over the bottom squared, and away you go. Okay, that's how you do it. Now listen, remember I told you with the product rule, it didn't matter as with the order, right? So you could do gf prime plus fg prime, right? When it's addition, it doesn't matter, but this is subtraction, right? And we know, for example, 5 minus 3 isn't the same thing as 3 minus 5. Those are opposites. So it's really important that you have the order right here. It has to be low d high minus high d low. That's why I had the way of memorizing it, because there's more order specific things you need to do here than there is with the product rule. Okay, so I really encourage you, if you need to, no judgment at all, please go ahead and rewind and go back through and make sure, if you don't at least understand both of these things, please make sure you have a solid way to do it, whether that be simplifying, which is the method that we could have done with this problem coming into the day before I had taught anything. So like if we had done this at the beginning of class, or the quotient rule, which we learned during class that you could have used. Please make sure you have a way of doing that. All right. So if you need to, please go ahead and pause the video so you can rewind. And then in a moment, I will move on to the second of the two problems. All right. So the second problem says this: the percentage of families that were married couples with children before 1970 and 2010 is approximately given by this function, such that 1 is less than or equal to t, which is less than or equal to 5. T is measured in decades, and t is equal to 1 corresponds to 1970. How fast are the percentage of families that were married couples with children, here's the big word, changing in 2010? How much is it changing? Okay, so a couple things that were tough for people. One, and I completely understand, because for a second I was like, whoa, what's going on? 1 is 1970. So the number we're going to want to plug in the end, we want to think about that. So 1 is 1970, 2 is 1980, 3 is 1990, 4 is 2000, and 5 is 2010. Okay, so that was kind of one tricky area. The second tricky area is like, what the heck do we do with this? So let's think about this. I want to know, how fast was it changing? So and I said this on a couple people's quizzes in the feedback, how do I measure change? Using the what? It's using the derivative. The whole point of the derivative is to measure change. I know I'm using the derivative because I want to know how much is it changing in the very instant that we get to 2000. So it's the instantaneous rate of change, as opposed to the average rate of change, where I would say, how fast was the percentage of families that were married with a couple of children? So if I said changing between 1970 and 2000, that would be average rate of change. But if I say changing in 2000, that's the instantaneous rate of change. So average rate of change is between two moments in time, and the instantaneous rate of change is at that one moment, right? So we looked at previously secant lines, which represent the average rate of change, versus tangent lines, which represent the instantaneous rate of change. And so what we need here is we need the derivative, because I want to know at that one moment in time what's going on. So essentially what I'm asking you to find is the derivative of this function. So there were two ways, and again, the two ways you could do it is the simplifying, so knowing this is t to the negative 0.27, okay, or using the quotient rule. So again, I'll do one at a time, okay. So here was the tricky part. I'm not going to show you the specific math, okay. You're welcome to do this on your own time and kind of try to figure out what the actual numbers are. I wasn't concerned with, can you tell me it's, what I'm concerned with is, can you show me that you know the rules that you would use in this position and can you use that to problem solve? I know your calculator can probably figure this out, so that's why I'm not interested in what's going on with the calculator situation. So here what we want to do is we want to do this. If we're going to use this rule, well, what we're going to do is first, we're going to factor out the constant, because the constant times a function rule says that if you have a constant in the function you're differentiating with that's being multiplied, like 49.6 is, and it doesn't have to, and it's always going to be the same value, right? This will always, it doesn't matter what t is, you're always multiplying by 49.6, no matter what you make t. You can factor out that constant and only work with the part that depends on t. And this makes it a lot nicer. Okay, so we'll have 49.6, and I'm just going to put a harder bracket in here because I'm going to do the derivative, times, so we bring down the power, we drop our variable, and we subtract 1, and this is the derivative. I would actually take this as a derivative in a case in which you are not allowed to use calculators, because this is not doable without an actual calculator. So if we wanted to, we could pull up our calculator and we could actually try to do this out. So we could do 49.6 times 0.27 negative, okay, and it's about, so you get about negative 13.39, okay, t to the negative 1.27. You could do it that way. This is what I would expect to see more on a test where I say you may use a calculator. But in this case, because you cannot use a calculator, you are not required to do that. Then the final step is, and I'll show you this in a second, but let me show you the other way to do the derivative. So here I'm not going to color code as much. If you want the color coded version, I just did that in the last problem. So I've got low. Now here it stays positive 0.27, because the reason is I'm not moving it up with the 49.6. I'm actually leaving it in the bottom. I didn't move it. I'm just using it in the quotient rule. So low d high minus high d low over the bottom squared and away we go. Okay? So you can see, look, this is a constant, right? 49.6, it never changes. If you were to look at the graph of f of x equals 49.6, it's always staying the same. You plug in 1, 49.6. You plug in 2, 49.6. You plug in 100 million, 49.6. So the 49.6, the derivative is 0. So therefore, everything is 0 because you're multiplying this by 0. Over here, what you get is you get negative 49.6 times times 0.27 t to the negative, and you'd subtract 1 and you'd get 0.73 over t to the 0.54, and the reason for that is because it's a power to a power, so the powers multiply, what I've heard called fly high multiply, okay? And then you'd run into a similar problem as you did here, right? So you'd basically get negative, right, if you really want to simplify. But then you can simplify this because it's a see, this is multiplication. So now these can cancel. And because of the quotient rule with regard to powers, these will actually end up subtracting, because when you divide a power by a power, you subtract them. So it becomes negative 13.39 t, and negative 0.73 minus 1.54 is negative 1.27. So you see we get the exact same thing we had before. So that was what most of the credit went to. So this is saying at a particular point in time, this is how fast the percentage of families that were married with children is changing. So at 0, it's not changing at all. We literally just started. And actually 0 is not defined. So at 1, it's going down. If you plug in 1, you'd get 1. So it's going down by 13.39, etc. But now I'm in 2000. So in 2000, t is equal to 4. So for the purposes of this quiz, all you had to do was show me something like this. Show me plugging in the 4. Or you could have done negative 13 point, whatever we got for that. This is all you had to show me, because if you plug this into your calculator, it is going to give you a specific number. Again, I'm not so concerned with that. I would encourage you to seek that out on your own. But what this is essentially telling us is when t is equal to 4, which in context is the year 2000, how fast is the percentage of married couples with children changing? This is your answer. Okay, again, on a test where you have a calculator, you would be expected to type that in and get the answer. On a quiz without a calculator, I just want to see that you're able to show me what am I actually doing, and then how would I actually get the answer, right? Because you being able to put this into a calculator is not important to me if you compare it to the idea of getting to that point, right? Being able to identify, 1, we need the derivative. 2, this is how we get the derivative, either of these two methods. 3, we have the derivative. I want to plug in 4 because I want the instantaneous rate right when t is equal to 4. Okay, two mistakes I saw in this. 1, people are doing the average rate of change. That's not really what I want. Okay, so some people plugged in like they did like p of 4 minus p of 1 over 4 minus 1. So that is saying that's the first question. So p of 4 minus p of 1 over 4 minus 1. That is the average rate of change between 1970 and 2000. Okay, it's not the same thing because that is what we'd call a secant line. So if this was going to, let's say, and I don't know this is true, let's say this is my function right here. Okay. What I don't want is, I don't want a secant line. A secant line just connects any 2 points. I want the tangent line. The tangent line comes and it touches the graph just at that one special point. Okay, like the blue line. I know it's not the perfect diagram, but I want it right at 2000, so I need the instantaneous rate of change, which is given by the derivative, and the derivative is calculated one of these two ways. Now, if you think about this, looking back on it, we got to think about this because this is an important skill as we progress into the semester. If we think about the homework quiz, right? So the homework quiz was on 9394. So if you think about it, right, I'm probably going to ask about derivative. 93 and 94 focus on derivative. So I'd expect you somewhere in there to use the idea of derivative. And this is going to come later on down, right? So next week, we're going to talk about applications to economics. There's going to be profit functions, cost functions, and revenue functions. So if we learn about that, then I would expect, like, yes, a cost function is going to show up, a revenue function, or profit function. Those might show up in some form in the next week, okay? So look, I hope you found this to be a helpful video. I know that these are not easy ideas, so I'm just going to keep encouraging you to send me problems over the email. So as of right now, you can reach me at robert.moray, M-O-R-A-Y, @umb.edu. I get those emails right on my phone, okay? Send me questions with pictures, okay? So send me a picture of your work, okay? And then say, I'm lost on number 3. And send me a specific question, because if the more you can send me, think about it like this. A lot of you are visual learners, right? So am I. I can't see what's going on in your head. But if you show me the work, then I can know, 1, what were they doing? 2, how do they approach it? So therefore, 3, what are you doing well? Where do you need to improve? Then 4, how can I guide you towards that improvement? So I promise you this, the more you show me, the more I can help you. Because I can tell you, as a general rule, the students who are the most successful in my classes do stuff like this. And I want you to be successful. I know you can be successful. And if you've seen this whole video up to this point, that's showing me, to me, that you're committed. To watch a video this long that goes into this detail, that's commitment. So let's keep it going and send me those questions so I can help you, okay? So you have this email anytime. You can feel free to stop by office hours or come before class anytime. But just, keep a positive mindset. And remember, no matter what, you can do it, okay? Thanks for watching. Have a wonderful day. And don't forget to love math.